In this video, we talk about products of prevarieties. So we have seen that when U and V are affine varieties, then also U cross V is an affine variety. But now what about products of prevarieties? So of course we can take the set X cross Y, but how do we give it the structure of a prevariety? So the first idea is we have these nice gluing constructions. So maybe we just construct it from gluing open patches, which we understand. Because if you're given affine open covers ui of x and vj of y, then, well, we can just take these products of the affine varieties and then glue them together to obtain x cross y. So it turns out this will work, but the problem is, how do you show that the result is independent of choice of covers? So what you could do is you could say, well, choose a second cover and then prove kind of by hand that these two things are equivalent. But in fact, a much nicer thing is to use a second idea. And this is more the uniqueness part of this product construction, because it's possible to characterize the product by a universal property. And then by checking that this construction here satisfies this universal property, we automatically get that it's independent of choice, because constructions classified by universal properties give unique up to unique isomorphism results. Okay, and so we do need to formulate this universal property, and it is one which we have already seen before. Namely, if x and y are prevarieties, then we define a product of x cross y as a prevariety P, the product, together with morphisms, pi x and pi y, from P to y and x, like this. And they should satisfy universal property, namely, well, for any z prevariety and morphisms to x and y, there's a unique morphism f from z to p, such that this diagram commutes, such that if you first go f and then pi y, you get fy, and f composed with pi x gives you fx. So we had seen this here before for affine varieties. And the slogan as there was that giving a map to a product is the same thing as giving a pair of maps to x and to y, respectively. As a side remark, note that basically this entire definition here makes sense in any category. As long as you know what are the objects and what are the morphisms, you can always write this down. So if you want, this defines for you in any category what it means to be a product of two objects. And that's a very useful thing to keep in mind. And here, again, if you want to look it up again, this here is the place where we check that when x and y are affine, then this property here holds, at least when the domain is an affine variety, because back then we only knew about affine varieties. Okay, so we also keep this in mind here. And then, well, we just construct these products. So we have a proposition telling us that if x and y are prevarieties, then they have a product P in the above sense, and it is unique up to unique isomorphism. So in other words, if you have a P, so this diagram here, and you have another product, this would be a diagram like this, then the claim is there's unique isomorphisms F from in this direction and G in the other direction, such that, well, first of all, they're inverse to each other, and the diagram here commutes, so that, for example, if you first go pi x prime, if you first go f and then pi x, then you get pi x prime, and so on and so forth. And so this unique product, then we can just denote by x cross y. And instead of starting with the construction and checking uniqueness, let's first check the uniqueness. So if one exists, then, or if two of them exist, then they're isomorphic like this. And so for this, you just observe that, well, you can use the universal property of P, because if you take Z equals to P prime, then, well, this space has a map to X and has a map to Y. And so by the universal property, there exists a unique map F, as in this diagram here. And by the symmetric argument, you swap the roles around, you also get a unique map G, such that all of these commutation things hold. And the only thing that you need to check is that they are inverse isomorphisms to each other. So you want to check that these two compositions give the identity respectively. This finishes the statement that F is an isomorphism, and then also the uniqueness. And so for the proof of this claim, now we just start manipulating formula. So basically, we want to check that G composed with F is the identity. So let's see what this map does after we compose with a projection operation. And well, then we'll use associativity, and then you see here you have pi x prime composed with G. But by the definition of G, G was the unique thing such that composing with pi x prime gives you pi x. This would be the error which is here. So we can replace this here by pi x. And then F, by definition, was the unique thing such that composing it with pi x gives this pi x prime, this map from p prime to x. And so this here is pi x prime. And then we can write pi x prime in a fancy way by saying it's pi x prime composed with the identity of p prime. You can always add the identity like this. And similarly, just the same kind of argument shows that G composed with F, if you compose it with pi y prime, you get pi y prime composed with this. So why did we do this strange thing? Well, we want to conclude that two morphisms from p prime to p prime are isomorphic or are the same, namely G composed with F and the identity. And what these two things show is that these are two morphisms which have the same composition with the two projection maps. And by the universal property of p prime, giving a morphism to p prime, this is uniquely determined by the two compositions like this. And so since they have the same things, they must be the same morphism. And so we have checked that G is a left inverse of F. And similarly, you can check G is a right inverse of F. And so indeed, they're inverse maps to each other. Okay, so this was the uniqueness, and this follows the very general pattern. So basically every time in algebraic geometry and also beyond, if you define things via such universal properties, all the proofs will kind of look similar to this, and they will always be unique at least. Okay, and then now we need to roll up our sleeves and actually construct this P explicitly, and then we return to the first idea that we have, namely we cover X by some affine opens U, I, and Y by some affine opens Vj. And then we have these products Ui cross Vj. So somehow here, look at this picture, which of course, well, I swapped the order of U and V, but never mind. So somehow this, I guess, sorry. This should be Y, this should be X. X is covered by the Ui, Y is covered by the Vj. And then we have the, for example, Ui cross Vj. This is a subset of X cross Y. And similarly, Ui prime and Vj prime is another subset. And the idea is you glue them on their overlaps. That's how gluing works. And what are the overlaps? Well, these are these regions. And well, you can check this is just the same thing as intersecting Ui and Ui prime cross Vj and Vj prime. So this is this overlap. And how do you glue them? Well, you just take the identity maps. Because, well, they do sit all inside this nice ambient just product X cross Y. And the identity maps, of course, satisfy the inverse of the identity is the identity. And if you compose two identity maps, you get an identity map. So these were these conditions A and B that we needed for the general gluing operation. And so we do get a glued pre-variety P, which is given by just X cross Y as a set. And then we have constructed P, but now the data of the product also requires these projection morphisms. And well, we do have projection morphisms from UI cross VJ, first of all to UI and to VJ. These existed because this we treated in the case of affine varieties. And UI sits inside X as an open sub-pre-variety. So we do get a morphism. So this is kind of an open embedding. So this composition here is a morphism to X. And then these morphisms, they fit together, of course, again on these overlaps. And so they glue two morphisms from all of P to X and all of P to Y. So we had this kind of lemma which says that morphisms of ringed spaces glue together. And this we now do. And so we got ourselves a candidate for our product P, and we got ourselves the projections. The only thing left to do is to check that our construction indeed satisfies the universal property. So let Z be any pre-variety, and given two morphisms to X and Y, now we want to define the map from Z to the product, which has the right compositions with the projections. And well, as a set, we really don't have a choice. So somehow f of an element of Z must go to fx of Z, fy of Z in this product. This is the only chance because, I mean, knowing the projection to X and Y of an element of X plus Y determines it uniquely. Somehow this is the only set theoretic map which can satisfy the condition. So what is left to show is that F is a morphism. That we must check. And then another general property of morphisms is that we can check whether a set theoretic map is a morphism on an open cover of the domain. So that's a lot of times this is the move, go, if you want to check something is a morphism, go to an open cover. And well, how do we get our open cover? We want to return to the case of affine varieties, which we know. So certainly we have these UI cross VJ sitting here. And we want to first restrict to the pre-image of this inside Z. And first claim is that the pre-image here is a nice open subset of Z. And to see this, just note, well, what does it mean to be in the pre-image here? It means that first of all, you must map to UI when restricted to X. Sorry that everything's messed up. You must map to UI when you restrict to X. So you're an fx inverse of UI. And you must map to VJ when restricted to Y. So you're in here. And once you're in this intersection, you land in this green part. And so this just means that the inverse image of UI cross VJ is just this intersection of these two things. And now since fx and fy are morphisms, they're in particular continuous. So this thing is open, this thing is open. So this region here is an open sub-pre-variety of Z. And then this thing can be covered by finitely many affine open subsets Zk. This is drawn here now. And then if you restrict these morphisms fx and fy to Zk, then these, this of course you can do, and then you get maps from Zk to UI and Zk to Vj. And now we are in business, because now we have restricted everything to the affine case. Zk's are affine, the UI and Vj are affine. And so we can apply the proposition that we already mentioned before. And this is saying somehow if you have this affine variety and the maps to UI and Vj, then they fit together to map from the affine variety to the product. And so this thing here is a morphism. And on the other hand, this product here by the gluing construction, this is an open sub-prevariety of the glued variety P. So this thing is also a morphism. And so this composition is still a morphism. That was what we wanted to check. And then since the ZK cover all of P, again, we use a particular lemma to say that F is indeed a morphism. And so this finishes the proof. We have checked the universal property. So products exist and they are unique. And then the final thing to do is to have a short remark, which is again one of these kind of compatibility conditions, because we do construction left and right, and then we need to check that they behave well with each other. For example, in the following sense, if you have xy, and then you have a closed subvariety x prime inside x and y prime inside y, then on this product of sets x prime cross y prime, you have two ways to get a pre-variety structure now. The first is that, well, x prime and y prime, they're closed sub-pre-varieties, so they are pre-varieties in their own right. And so their product, using construction above, is one structure of a pre-variety. The other thing is that, well, x cross y, the ambient space, this has a pre-variety structure. And this is a closed subset here. And then, well, you can just take the structure of this as a closed sub-pre-variety here. A priori, this could be a different ringed space, but the claim is the identity here, so both of these maps are just the identity, give inverse isomorphisms between these two possible ways. So you can first take sub-pre-variety structure, then product, or you can first take product and then the sub-pre-variety structure. And this gives the same thing. And to show that, well, you already know what the maps are. They are the identities. Of course, the composition of 2 times the identity is the identity. The only thing to check is that these are morphisms. And to show that these are morphisms, you can use remark 5.12 about the compatibility of somehow if you have a map from here to this, which factors through this set, then also this here is a morphism, and the universal property of products to construct these morphisms and check that indeed both arrows here are given by a morphism. Okay. So that's everything about products of pre-varieties.